So today what I thought I'd do is something I mentioned I would do on the discussion boards earlier this week, which is sort of walk everyone through how a sampling distribution works. And there's plenty of different videos that you probably could have found on Khan Academy or anywhere else. Maybe the book made plenty of sense to you, but I wanted to make sure to do a working example that we'll do in Excel here and then also in a program that I use for statistics. So you'll really be able to visualize what a sampling distribution is, what it means, and then how does it lend itself to understanding the central limit theorem. Okay, and all this is Chapter 8 that you would have been working on this week. So this is a concept that maybe you're still struggling with. Make sure that you watch this all the way through. You can rewind, watch it again, do whatever you need to do. Okay? So what I'm going to demonstrate is the idea of what a sampling distribution is. Okay? So what you can see here is I've already gone through the trouble of setting up an Excel file, and here I have some random variable x, right? And it's discrete. You can see that you can count it, but let's imagine for the purposes of what the chapter is talking about, it could be discrete or continuous. It doesn't matter. The sampling distribution is the same premise either way. And what this random variable is it's a sequence of numbers. It's a uniform distribution. I made sure it was uniformly distributed, containing all the numbers from 1 to 1,000. Okay, so this is a uniformly distributed random variable, and if you wanted to see what the histogram looks like, this is the other program I'm using here. It would look like this, right? Where every single value is equally likely to happen, so it's just one big rectangle of a histogram. Alright, so that's what we're working with. And what I'm going to demonstrate here is if I sample from this uniform distribution, and each sample I take and record the average of that sample, right? What I'm doing is constructing a new random variable, which is usually called capital X bar in your book, and other places that you would see it written. And what I'll be able to do is look and see how for each sample, and I take the mean, I can see how those means are distributed. So I'm going to collect and construct a sampling distribution. Okay? So, earlier on in the book you probably would have seen one of the examples they said of how to take a random sample from data in Excel. And so what I'm going to do, let me zoom in just a little bit here. What I'm going to do is I've populated this entire column, the whole length of this uniform variable, with just the rand function, which is it's a uniform distribution random number, and so that allows me to sort on these, and every time I do anything I can hit enter, I can click around, and it all changes these. So I can sort on this column, and then these numbers, if it's at the top here, will be different every time, and I can sample out of these. Okay? So, for demonstration purposes, here's what we're going to do. So here's what we know so far. So x is a uniformly distributed random variable from 1 to 1,000 in this example. I have the random thing here, which you can ignore. I'm only going to use this to pick my sample, basically. And what I'm going to do is I'm going to use a sample size of 10, so these first 10 numbers that show up here after I sort this sampler, basically, I'm going to calculate what the average is, and I have it here so I can see it more easily. Right? I'm going to do this, then I'm going to change the sample it again and take a new average. Change the sample again and take a new average for any sample size of 10. Okay, and we'll start there and I'll demonstrate what the difference is. But what I want to show is how you can go about constructing a sampling distribution so that the process makes more sense. Okay, so first thing I'm going to do, I have all this filled out, I'm going to sort smallest to largest, and now I have a different set of 10 numbers that's not here before, and they're all random. They're random because these numbers that were used to select these are random, right? Random sample of these 10 numbers, the average, this sample mean, x bar, is 620.1. Okay, so that's my first entry in this new random variable, capital X bar, which is a collection of all the sample means that I could find. Right? So, I sort again, and I have a new sample mean showing up over here. I have it again calculating these top 10 just so I can see it more easily. So this is 606.7. Okay, do it again. 381.3 is my new sample mean. Alright, do it again. And I have 711.7 as my new sample mean. And I can do this on and on and on and go all the way down. I mean, I can take, any number of samples that I want of sample size 10. So each sample from the population, I'm taking a sample size of 10, and I can take however many samples I want, right? So right now I have 4. I could keep going all the way to 1,000, to 10,000. I could stop at 20. I could stop at 30, whatever, right? And so what I'm doing is I'm taking a sample mean of size 10 for each different sample that I take, and I'm recording those sample means as a new variable. Alright, so I'll take a few more just so I can demonstrate what I'm saying. So 461.7 is another sample mean. 284.8 is another sample mean. I'm pulling it from here. Right? Oops. Well, large or smallest doesn't matter. 572.5. Isn't that what I mean? So see, I'm making a new variable out of means from this variable if I take samples of 10 at a time. Okay, and again, this is uniformly distributed, so this population variable here, x, is distributed like this, right? Uniform distribution, one big fat rectangle. This variable is going to, according to both how sampling distributions tend to look as well as to prove the central limit theorem, this is going to start to look like a normal distribution. So even though this is a uniform distribution, this could be any distribution shape, honestly. It could be normal, Poisson, hypergeometric, whatever. The sample means drawn from any distribution will, if the sample size is large enough, start to look like a normal distribution. Okay? So, what I've done here is in this program here, I won't bore you with the code that I wrote and everything, but what I've done is I have, instead of 1,000 for the size of this uniform population, it goes to 10,000. So it's 1 to 10,000 is all equally likely to be selected from this population. And I took a bunch of different samples, I think 500 samples, of different sample sizes and made distributions out of them for you to see. Okay, so again, this is the population. This here is a histogram of the population for variable x, right? Uniform, 1 to 10,000 or what it could be. Now, if I took a sample size of 2, so I'd take 2 members out of this population and I find the mean, and I did that 500 times, so I took 500 samples of size 2 and then made a distribution out of those means I found. Well, you can see that even though this population is uniformly distributed, it's a big rectangle, well, the sample means start to sort of curve, right? This isn't a very clear distribution, big bell shape that we're used to yet, but you can see that it's certainly not uniform. There's different probabilities of getting each different possible mean, okay? And the specific values don't matter. The point is to understand the shape of the graphs, okay? Now, this is if I take a sample size of 2 and calculate the mean for each time I draw it. If I take a sample size of 3, the distribution changes a little bit, the tails get a little thinner, it's not super noticeable, but you can still see that it's it's sort of a mound-shaped distribution and not uniform, right? If I take a sample size of 4, all of a sudden, we've lost some real outliers here, and the distribution is starting to look like a bell curve. Okay? With me so far? And again, you can back this up and you can look and see how I'm changing this. And then in a minute here, what I'll do is I'll slowly click through each of these different growing sample sizes, and you can see how the central limit theorem is sort of being demonstrated. Okay, so this is a sample size of 4. If I draw a sample size of 4 from the population, calculate a mean, and then record the mean, and then graph that distribution of those means I found, this is what this would look like. Okay? What if I take a sample size of 10? Well, if I take a sample size of 10, now you can see that we've really tightened up. So I'm keeping this axis is always 0 to 10,000, so you can see how close it's getting. So suddenly we go from sample size of 4, now we take a sample size of 10, and those means are very, very tightly packed, and they're definitely normally distributed, right? It kind of comes up like a bell, tops out, comes back down, and then tapers off into the distance, right? So this is for a sample size of 10. A sample size of 50 looks even closer. Now we're very closely bounded. All the means that were found here are within about 4,000 to 6,000, right? So the random variable itself takes on values from 1 to 10,000, but if I take sample size 50 and then sample 500 times, you'll find that all of those means only fall within these. Because my sample size is getting bigger and bigger and bigger, my sampling distribution is getting smaller and smaller. It's getting tighter. It's becoming much more normally distributed. Okay? If I take a sample size of 100 and do the means, you can see that it didn't get much tighter, but more of the outliers got pushed to the middle. So you can see that I was sort of bell-shaped here, and now it's a much tighter, taller bell. So more likely that I will find a mean that's somewhere around here, which is the actual mean of the population distribution. Okay? And that's what the central limit theorem says. The central limit theorem says that if you increase your sample size, as the sample size tends towards infinity, basically, then what's going to happen is your sampling distribution is going to, if it's for the mean, will start to approximate what the population's average is, population mean, and the variance, right, how wide this distribution is, will get smaller and smaller and smaller as you increase your sample size, right? And that's what the central limit theorem says. So again, I can even take sample size of 500. So I take 500 members out of that 10,000 population, and I sample it 500 times, and this is what my sampling distribution looks like. Incredibly narrow, right? And very, very close to the population mean, which is 5,000. Right? The population mean is 5,000 because I have, well, this is values between 0 and 10,000. So my population mean is actually 5,000. I know that in the population. And if I sample enough and take sample averages, I'll notice that those will tend to be very, very close to my actual population mean if my sample size is big enough. Okay? And generally the rule of thumb, especially in business, is that as long as your sample size is above 30, as long as your sample size is above 30, you can confidently think in terms of drawing a sample and being confident that it represents what the population mean is, as well as some other neat tricks we'll learn both later in this chapter when you're making confidence intervals and for the rest of the material in the semester. Right? So again, I'm going to back up here. So this is the population. Okay, I'm going to click through these so you can see how the change goes as I increase my sample size. I'll do it a few times. Population, uniformly distributed. If I take sample sizes of growing size, they become normal. The means are becoming normally distributed. Sample size of 2, 3, 4, 10, 50, 100, and 500. You see? The sampling distribution became much, much tighter with a lower variance and a lower standard deviation as my sample size increased. And it also began to become a better predictor, an unbiased predictor of the population mean. The variance will eventually, as this sample size becomes infinity, basically, this only sample mean you could draw is the population mean. So a bigger sample size gives you a better approximation of what the population mean actually is. Right? And that's the premise of statistics, if you haven't been following along so far, is that we draw samples, calculate statistics which describe those samples, and use them to infer things about the population at large, because we can't always know what the population is, so we estimate it. Okay, I'm going to go back and click through this one more time, even though you can back up and view it at your leisure. Population, draw a sample, calculate the averages, and then distribute the averages with a sample size of 2, 3, 4, 10, 50, 100, and 500. And that's how sampling distributions work. And that is how you can see a defense for what the central limit theorem is. Okay? I'm happy to answer any questions you have. Please email me if you do have any, excuse me.